Every story about modern AI eventually runs into the same wall: the hardware. The models are software, but the thing that decides who gets to build them is a chip. So today, why does AI run on graphics cards? And why does one company own almost the whole market?
It's a great question because the answer isn't really about graphics at all. It's about one kind of math done a staggering number of times at once. Once you see why that shape of math wants a particular shape of chip, the rest falls into place.
Let's start there. Why a GPU and not the CPU that's already in everyone's computer?
Because a neural network underneath is mostly one operation: multiply a big grid of numbers by another big grid and add up the results. That's matrix multiplication. And it breaks into thousands of small multiplications that don't depend on each other. They can all happen in the same instant.
And a CPU is bad at that?
Not bad, just built for the opposite job. A CPU has a handful of very fast cores that race through complicated tasks one after another. A GPU has thousands of small cores doing the same easy multiply all at once. So for deep learning, training on a GPU is commonly reported at roughly 10 times a comparable CPU. And modern chips add tensor cores tuned just for matrix multiply.
Okay, so AI wants parallel chips. But why does it specifically want Nvidia's parallel chips? They're not the only company that can etch silicon.
By most 2025 estimates, Nvidia holds somewhere around 80 to 90% of the AI accelerator market. The hardware is excellent, but that share isn't really about the hardware. The moat is the software layer that sits on top of it, called CUDA.
What is CUDA exactly? And why is it so sticky?
CUDA is the toolkit that lets programmers actually use those thousands of cores. Nvidia shipped it back in 2007, so it's had a 15-year head start, and reportedly, millions of developers and nearly every AI framework are built on top of it. Switching to a rival chip means rewriting and retesting that whole stack, so most people simply don't.
And which chips are we actually talking about right now?
The workhorses of the last couple of years are the Hopper generation, the H100 and the memory boosted H200. The newer generation is called Blackwell. Nvidia has described Blackwell as a very large jump in inference performance over Hopper, though exact multipliers depend heavily on the workload, so treat any single headline number with caution.
You keep saying memory. I thought the whole game was raw compute, more multiplies per second.
That's the surprise. For running a model, Inference, the bottleneck is usually not doing the math, it's feeding the math. Every token, the chip has to haul billions of weights out of memory and into the cores. And that move is the slow part. Researchers call this the memory wall.
How big has that gap between compute and memory gotten?
Google researchers reported that over roughly the last decade, chip compute grew about 80 times, while memory bandwidth grew only about 17 times. So the cores keep getting hungrier than the memory can feed them. The answer is a special, stacked, very fast memory called HBM, high bandwidth memory, bonded right next to the chip.
And that HBM is its own bottleneck now, isn't it?
It is. HBM is hard to make and only a few firms make it, and demand reportedly grew well over 100% in 2025, with supply said to be sold out through 2026. So a chip's value is increasingly about how much fast memory it carries and how quickly it can read it, not just its peak multiply rate.
So if Nvidia owns the market, is anyone actually competing? Or is this just a monopoly story?
There's real competition, just not much dent in the share yet. Google builds its own TPUs, used heavily inside Google. AMD makes a competing line, the MI300 series and the newer MI350. The big cloud companies design their own chips, like Amazon's Trainium, and reportedly, those custom ASIC chips are now growing faster than GPU shipments. And newer entrants like Grok and Cerebrus build chips aimed squarely at inference, betting on raw speed and cost per query. But the wall for all of them isn't the silicon. It's CUDA's ecosystem.
Now the part that turns this from a tech story into a world story. Governments care about these chips. Why?
Because if compute is what builds frontier models, then whoever controls the chips controls who can build them. Starting in 2022, the United States restricted exports of the most advanced AI chips to China, treating compute as a strategic resource, like a controlled material, not just a product.
And Nvidia responded by building weaker versions just for that market?
Exactly. Chips deliberately slowed to fall under the limits. The H800 was an H100 with its chip to chip bandwidth cut down. Then it too was restricted in late 2023. The H20 was an even more stripped back Hopper part for China, and its status has flip flopped, licensed, paused, then allowed again, as the rules kept shifting through 2025 and into 2026.
Meanwhile, the people who can buy chips are spending like there's no tomorrow.
Wildly. Estimates put combined hyperscaler capital spending in the range of $600 billion plus for 2026, the bulk of it aimed at AI infrastructure. When the scarce input is chips and fast memory, the rational move is to buy as many as you can before your rivals do. And that's exactly what they're doing.
So bring it home. What's the one thing to take away from all of this?
It's this. The model is software, but the ability to build one is hardware. GPUs win because AI is parallel math. Nvidia wins because CUDA locks in the ecosystem. Memory bandwidth quietly sets the ceiling, and chips have become a strategic resource that governments fight over. Compute is the real bottleneck of the AI era, and whoever controls the chips shapes who gets to build the frontier.